Okay, today we are going to discuss the typical organization of a compiler. Compiler as basically given a source code written in string. String is basically an array of characters or array of bytes, and the source code you're going to be given is just a string of characters, WHILE blah blah blah. And your compiler is then translating the given source code written in string into some machine code, which is also a string. But it is not meant to be read by humans. It is meant to be read by machines, so it is written in bytes. So this string is just an array of bytes. So as you can imagine, compiler is not at all doing some trivial jobs. It is performing a non-trivial translation from source code into machine code. So it is typically consisting of multiple passes. Each pass of the compiler is performing its own job. For example, the first pass, parser, is translating the source code written in string into the source code written in AST or abstract syntax tree. Abstract syntax tree is basically a mathematical object that is represented in a computer that is much more easier to deal with than strings. So that is basically the object of the later passes rather than strings. And later, after the source code is parsed into some mathematically well-behaved object, and it is going to type check. That means the compiler is checking whether the programmer is committing an obvious mistakes or not. And then it is going to generate an IR from the AST. IR is intermediate representation that is between the source code and machine code that is meant to be easier to perform optimizations, basically. So in order to perform many optimizations afterwards, it is going to perform IR gen first. After performing optimizations, it is going to generate assembly, for example, x86, ARM, or RISC-V assemblies. It is meant to be human readable, so it is equivalent to machine code. It is mostly equivalent to machine code that is actually executing in your CPUs, but it is meant to be human readable. And this human readable form of assembly is going to be printed into machine code that is actually a bit stream, the array of bytes that is actually executing on your CPUs. So we are going to look into each part of the compiler one by one, starting from the parser. Parser is, as I said, translating source code from AST, source code from string to AST. The main difference between the two representations are that the string is one-dimensional object. It is basically an array, one-dimensional array of characters, WHILE blah blah blah. On the other hand, AST is a two-dimensional object, which is tree, basically. So, for example, this whole program is a statement at the root here in the right figure. And it is consisting of two sub-statements, that is while and return. And while is in turn consisting of a comparator, b is not equal to 0, and also it has body that is branching based on the condition that a is greater than b or not, and blah blah blah. So basically, all program as you imagine in your mind is two-dimensional objects consisting of nodes and edges, and which is basically a tree. But it is written in the string, in the file. So we need to translate this one-dimensional object to two-dimensional objects. After parsing the source code, we need to type check. Type checker is checking if the given program is grammatically correct. So it is not checking whether it conforms to your some business logic or specification of the program, but it is just checking whether the program satisfies some grammatical rules. In English also, in Korean, we have some grammar checker, right? For example, there should be a subject, verb, objective, blah, blah, blah in English. And that they should be presented in that order, for example. And we can check that. So the job of type checker for programs is much easier than job of type checking or grammar checking natural languages, because as we saw in this previous slide, programs are written in tree, which is basically a well-defined mathematical object. So we can also type check in a mathematically clear way. The reason why we do type checking is that we do not want to deal with obviously wrong or obvious mistakes in the programs. For example, if the program does not return anything, if a function does not return anything, and you can know that at the before executing the program, it is more cost effective to reject just such a program. Oh, this program doesn't return. It doesn't do anything. So we do not deal with this code. Blah, blah. So by doing so, we can easily prune out obviously wrong or obvious mistakes. For example, this program that is declaring a function that returns integer, but it is assigned to 42, which is obviously wrong, because you're going to declare a function, but you're assigning an integer value. They are different things. So the compiler can deduce that, oh, this program is very wrong, and you're probably not meaning to write this code, and I'm going to reject it. And as a second example, here you're defining a function that just prints the value, and it has only one argument, x. But at later stage of your code, you may call this function with two arguments, 2 and 3, which is very wrong, because the foo is expected to accept only one argument, but you are providing two arguments. So compiler can say that, oh, your program is grammatically wrong, and you probably didn't mean to do that, and I'm going to reject this program, and blah, blah. So as I said, this is very crucial for your productivity. By automatically rejecting your obvious mistakes or errors, you can focus on your business logic better. So after type checking your program, you're going to translate your C program into intermediate representation, or IR. So recall that the source language is human-friendly and idiomatic and expressive, and the target language is machine-friendly, efficient and low-level. But both of them are not very well suited for optimizations, because source languages are making a lot of abstractions, and usually the compilers is difficult to find optimization opportunities inside this very rich code. And target languages are very low level, and it has all the small instructions that is executing a tiny job of computations. So again, it is really difficult to find optimization opportunities inside these target languages. So IR languages are meant to be optimization friendly by providing many features. For example, it should be very easy to recognize optimization opportunities inside this IR, and also it has a very regular and simple and small structure of the language constructs, so that it is not very difficult to write down the compilers. So here's an example. Let's say that this program in the left, that is meant to be written in high-level code, is returning the summation from 0 to magic. Magic is just a constant value for it too. And you're going to compile it to the code in the right side here. That is meant to be a pseudo assembly code. And this M is a memory location, in R is a register, but you don't need to know the details about it. The message here is that this program is very low level, and it is really difficult to find the structure of the computation here. Okay, the both form of the programs are not very easy to optimize because in this high level program, it is really difficult to notice that, oh, this is actually performing the summation, and we can just unroll this and get the value at once. It has too rich structure in this computation, so compilers is not very easy to recognize the structure of the computation. On the other hand, in the right side code, it is written in a very low level, and it's very difficult to find the computational structure as well. So we want to find some intermediate representation here, like this, that is representing the structure quite well. For example, this is looping over I from 0 to magic, and it is accumulating the value and returning A. Then by looking at this code, we can immediately see that, oh, there is some structure of the computation that is looping over the values, and it is getting the summations. So we can probably it is probably easier to apply optimizations by replacing this magic value with 42 and unrolling this loop, and then this replacing this A with some value that is summation from 0 to 42 and blah blah. So to summarize, so the source code, for example, C, Rust, and other program languages, it is very difficult to apply optimizations because of their too rich computational structure. On the other hand, in the right side code, that is meant to be pseudo assembly or some more low level x86 or RISC-V assemblies, it has too thin computational structure, so we cannot apply optimizations. But so in the middle, we want to translate this code in the source language into some intermediate representation in the middle here that is easier to perform optimizations, and then translate this code into this code to the low-level code. So that's the reason why we designate a IR, and we first perform IR gen before, instead of translating C to assembly directly. So let's look at the example optimizations that we can perform on the IR. So the purpose of optimizations is basically improving the quality of the program. For example, you want to improve code size, reduce code size, and reduce instructions to perform, and reduce the size of the memory you're going to spend, or the amount of energy you're going to dissipate. So here is such an example optimizations. The first one is register promotion. That is basically converting a memory access to a register access. So usually registers are meant to be more closer to the CPUs, so it consumes less energy, and it is much faster to access. On the other end, it has very small size. Register has only hundreds of spaces, while memory has gigabytes of spaces usually. So in this example, we want to transform this memory location like A and I into a register. So it is very easy to do so because I and A are not address taken. The address of them are not taken to the others, so we can be sure that, oh, only I am accessing the variables A and I. So there's no interferences from the other threads or other part of the program. So we can safely turn these memory locations into registers. So we can perform such an optimization first by performing register promotion like this. And after register promotion, we can easily perform other optimizations as well, like constant propagation or loop unrolling. So first of all, this program that is taken from this, and look at this code, and you can see that, oh, magic is just 42. So we can replace this magic with 42. So this arrow is performing the first optimization, replacing magic with 42. And at the later stage of the optimizations, you can also see that, oh, this loop is always performing the fixed number of iterations. It is iterating 42 times. So we can just safely unroll this loop, replacing this for loop with 42 instructions that is performing add. And afterwards, you can see that, oh, actually, we can just shrink all the computations into just one instruction. We can just replace the result of this summation with 903 that we already computed by the in the compilation phase. Instead of executing this for loop in runtime, we can execute this loop at the compile time and replace this value of A with 903. So by performing these two optimizations, or 3 or 4 optimizations, we can dramatically reduce the amount of code, the 4 lines code, into this just 1 line code, return 903. And furthermore, we can dramatically reduce the time we should spend on computing this, and the size of the memory, or the size of the amount of energy we're going to use. So one of the main difficulties in performing optimizations is the analysis about the non-interferences between other parts of the programs. Let's see an example of here. It is first reading from the memory location X and assigning the value of this value into the register A, and it's performing other operations. And again, it is reading X, the memory location X, and assigning the value of X to the register B. And we can see that you are reading the same memory location twice from X. Then we may be able to change this X equals X, B equals X by B equals A, because A is already the result of the load operations. But it should be, before performing these optimizations, you should analyze that in this code, between the reading from X to A and reading from X to B, you have to make sure that this code does not change the contents of the X. If here you're assigning some value to X, then this optimization will be incorrect because the value of X can be changed. So before performing this optimization, we need to reason about the fact that other part of the program that is here, it is between A and B, is not interfering with the value of X. Now let's look at the second example. This example is storing the value, the register value of A into the memory location X and doing some other things, and then storing the same value to the location once again. And you can see that, oh, you're storing the same value to the same location twice, so it is very inefficient. And maybe the second store can be removed. We can just replace the second store with a no operation that is performing nothing. It will dramatically reduce the energy consumption and the computation cost, basically. So you may want to do this, but you have to make sure that in between, X is not stored once again. If X is stored with another value in between these two stores, then this translation will change the final content of X. For example, in this program, in the last program, before optimization, X value should be A after this code. But after performing optimization, replacing the store with no operation, it can contain the other value that is stored in between the two stores to X in the optimized program in the right. So it can be different. So we need to prevent such a case by analyzing the part of the code that is between the two stores. So like these examples, we need to reason about the fact that the optimizations you're performing should not interfere with other part of the program. Only if your program is, your optimization is not changing the semantics of the program, you can perform the optimizations. So there are many ideas to reason about such non-interferences. For example, SSA or static single assignment or alias analysis or memory SSA and blah, blah, blah. And we're going to study SSA or static single assignment in the course later. Okay, suppose that we generate IR from the C source code and perform some optimizations. And now we have to translate IR into machine code, targeting on physical resources. Machine code is aware of physical resources, for example, the arithmetic units or the size of the memory or etc. So we need to, or size of the registers, most importantly, or the type of instructions you can perform. For example, x86 provides instructions, many instructions that perform the subtraction, integer subtraction. So depending on the situation, you can wisely choose which instruction to use from the architecture in order to optimize your performance. So such a thing happens in this ASM-Gen pass, translating IR to machine code, recognizing the physical resources that is available to the machine. So the most important thing to do in this ASM-Gen is register allocation. So usually in the IR, you're assuming there are infinite number of registers because it is easier to deal with. But in reality, there are only a finite number of registers. So you have to fit, or you have to map such an infinite number of registers into finite number of registers. And that is called the register allocation. Another important things to do for this IR to machine code gen, ASM gen, is instruction selection. As I said, there are many instructions in the architecture that is exploitable, and we need to choose instructions for each instruction for IR. I mean, we have to choose instruction in architecture for instruction for IR. So, for example, this load instruction that we use in the IR can be translated into the move instruction in x86 or LDR instruction in ARM. So they have different characteristics, and we have to choose which instructions to use for a particular IR instruction. So ideally, if you want to implement a compiler that targets on multiple architectures, it should be the only machine-dependent part of the compiler. So IR can be shared among machines or instructional architectures, but this ASM gen cannot be shared among multiple architectures because they have different numbers of registers, different instructions, etc. And in this course, in your homework, you are going to target on RISC-V, which is the recently developed open source and clean state RISC architecture, and it is getting momentum these days. And in my experience, it is much more easier to target on than x86 or ARM. So ARM and x86 has thousands of pages of manuals, but RISC-V only has hundreds of pages of manual. And later we are going to print the machine code AST to string, but we are not going to deal with the printer in this course. So to summarize, your source code is given as a string, and it is parsed into an AST by a parser, and then it is going to type checked, and if it is okay, then you're going to generate the IR from the source code AST. The IR's purpose is the performing optimization is easier. And you actually perform some optimizations, recognizing some interferences and analyzing interferences and recognizing optimization opportunities and replacing heavy instructions with lighter instructions and blah blah. And then afterwards, you're going to perform ASM gen, which is generating a machine code AST or binary or assembly. The main part of this ASM gen is recognizing the physical resources, hardware resources. And then you're going to print your machine code into the string. So that is basically the whole flow of a compiler you're going to build. So this structure is already provided as a skeleton, and the parser is also provided with you. So you do not need to implement your parser on your own. And you need to write down your IR gen on optimizations and some ASM gen. So these three parts are the main part of the homework: IR gen, optimizations, and ASM gen. So yeah, here is the summary of the things. Parser is translating one-dimensional object to two-dimensional object. IRGen is translating human-readable form or human-friendly form of program to optimization-friendly form of the program. And optimization is improving efficiency. ASMGen is targeting on physical resources. And printer is again translating a program from two-dimensional object to one-dimensional string. So afterwards, we are going to actually construct the IR and how to define IR, what we should do when designing IR, and how to implement IRGen and ASMGen and optimizations so that you can do homework. And furthermore, we are going to briefly discuss how to ensure compiler correctness. So in this slide, we discussed how to organize a compiler, but we didn't discuss the specification of a compiler. In what sense the compiler should be correct? How to ensure that your compiler is actually well translating your source code into machine code. So this is the topic of compiler correctness, and we are going to discuss this in a later lecture.